Testing. Okay. Hello. Okay, recording. Hello, Assalamualaikum warahmatullahi wabarakatuh, and good afternoon to our lecturer, Sir Hafiz bin Sakawi. And for today, I will explain to you about Lab 6, System Stability, and my name is Muhammad Hafiz bin Tamizaham. Okay, let's go through the lab sheet that have been given. Okay, this is the lab report, and this is the MATLAB. Okay, and firstly, let's go through the objective. So the objective of this lab is the student need to learn how to generate the plot magnitude from the transfer function, and the second objective is how to generate root locus from the system and compare it with Routh-Hurwitz method and verify the stability of the system. Okay, and this is the synopsis and equipment, and the equipment that we use is MATLAB software. Alright, and this is let's go to the procedure. Okay, this is the lab activity. So for part A, root locus and plot board magnitude. For number 1, part A 1. So for a system shown in below, by using MATLAB and the symbolic toolbox, find the root locus for the system, and the second is find the board log magnitude and phase plots for the system. Okay, this is the equation that have been given, and this is the example of the program that the lab sheet had given to us. So we can copy the code for MATLAB, and we substitute the value that have been given here. So negative A is negative 20, and negative BC is the value of 1750. Okay, so this is the code that I have done. Copy paste and then you save and run it. That is for part 1, and for part 2 is over here. It is the same. The difference is you need to change the board G grid on. You need to add, not need to change. You need to add the board G grid on. So as you can see over here, if I run the MATLAB, and you can see here is the code output. Over here for part A1. So here is the output over here, and this is the code, and this is the output. Continuous time 0 Paul gain model. Alright, and this is the graph. Okay, as you can see, I have done the results. I have passed the result of the graph in the lab report. And for the second one, as I said before this, the code for MATLAB already given in the lab sheet, so it is the same as this, and then you need to add in between is board G and grid on. Okay, so part A2 is over here, and you can see. Okay, if you run the code, and this is the output that been given, the MATLAB given. So this is the code, and this is the output. And okay, let me show you the command. Okay, this is the part 2A. Okay, as you can see, I have pasted the output in the lab report, and this is the graph that I have gained. Okay, so this is for part A. So for part B, as you can see, let's go back up. For part B, that is part B1. Alright, so this is for part B. So let's me read for procedure part B. Part B, that is Roth, Horowitz and root locus. So the number one is use MATLAB and the symbolic math toolbox to find the root locus of the following function. Observe the poles are in the right plane, in the left plane, and on the JW axis. Compare your MATLAB results. So the second instruction is I need to compare the results, okay, with the manual calculation by using the Roth Hurwitz. So this is the equation that have been given in the MATLAB in the lab report. So, and the third instruction is for the function above, verify the function whether in stable condition or not. Okay, so I need to verify it. Is it stable or not? Okay. I'm sorry. And this is the example for system that the code for MATLAB had been given in the lab sheet. So over here, so I use this and substitute the value to each question. So like here, number one, part B number one over here. So the number is 2 and the density, the numerator is 2 and the denominator is here over here, that is 1 2 3 1 and 5. So as you can see over here, I've done the substitute the value for the denominator, that is 1 2 3 1 5. So after you copy the code and paste the code and change the substitute the value to the each question that been given, and then you run the code MATLAB, run the MATLAB, and then you will get the results, the output. So the output that I have gained, so check the command prompt. So this is the lab 6 part B1. This is the output that I have. Saya dapat. So wait, part B1, part A1. Oh, this is the result for part A. So for part B, over here, yeah, over here. So this is for part B, part B1. As you can see, I have put it in the lab sheet, and the graph that I have gained over here, and this is the result that I gained. Okay, and this is the calculation that I have done manually to compare some other whether it is stable or unstable, that I need to verify it. So I have jot down the result, that is there are two changes signed in the first column. So the system is unstable because have two poles at RHS. So for part B1, the result is the graph is unstable because there is two poles at RHS. Okay, that is for part B number 1. For part B number 2, as you can see, as usual, as I said before, I'm sorry, use the same code and substitute the value. So for part B number 2, so I change the numerator. S is 1, 8 is 8. Okay, so the denominator is S1, 5, 5, 3, and so on. 15, 16, and 20. After that, just change the numerator and denominator, and then you run the code, and you will get the output, the result. As you can see over here. Okay, this is the result for part B2. Okay, I have put the part B output in the lab sheet. It is the same as the question: s plus 8 s power 5 plus 5s power 4 and so on. Okay, and the graph I get is like this, and as you can see in the graph, there are two changes signed in the first column, so the system is stable because have two poles at RHS. Yeah, as I said it before. For part 2 also it is unstable. Over here, as you can see, the manual calculations, there are two poles that are changed, and that have two poles in the RHS. So the result is to verify the poles is unstable. And for part 3 it is the same. So I need to change the numerator to 100, and the denominator is 1, 3, 8, 18, 20, 24, and 16. And as you can see over here is part 3 B3, so 100, 1, 3, 8, 18, 20, 24, 16. Okay, and then you run the code, the MATLAB, and you will get the output like this. And as the output for part 3B is this. Okay, and the graph I get is like this. So it shows that the system is marginally stable because there are four poles at imaginary axis. So that concludes that B3 is stable rather than unstable like before this. Okay, so this is the calculation. As you can see, it is all positive, the poles, and to verify it that the system is marginally stable because have S outposts at imaginary exists. Alright, that's all for the part A and part B for lab 6. So as discussion, we conclude that this week's lab shows that we as students must learn and understand what is plot magnitude from plot magnitude from the transfer function. In part A, we learn how to identify the root, locus, and plot board magnitude by using MATLAB and manual calculation. And as for part B, we learn how to calculate by using root Hurwitz and root locus from the function given by using MATLAB. And the symbolic method box, we find the root locus. From the root locus, we can observe the poles that there have three situations that I have shown before. For part B, they are unstable. This is unstable. Part 2B, B2, and for part B1 is system is unstable because have two poles. Yeah, for part 1 also unstable. Only part 3 is stable because four have four poles and imaginary exists. Okay. Okay, this is for discussion, and for the conclusions, as in objective, that I've concluded that after done this lab, I understand that how to generate root locus from the system, and I can compare it with Ruth Horowitz methods and verify the stability of the system. Okay, there are three situations that have been recorded in the result of the lab, which is stable, unstable, and marginally stable. So we can see the position of the poles to determine this situation. Lastly, we learn how to generate plot board magnitude from the transfer function. Okay, that's all for today's lab 6, system stability. Okay, thank you to our lecturers, Hafiz bin Sarkarui, to spend his time to watch this video and to assess our lab. And thank you to our lecturer. Okay, that's all for today.